Let's wait for all the others. You can hear me, guys? Okay. That's nice. So I should start, Giorgio? Okay. Okay. Okay, guys. So today we are going to speak about projective ICP. That's a really similar problem to what you see with both Giorgio and Barbara last time. Just that in this case we will have to deal with measurements that came from a camera. Okay. That's not a classical exercise in the sense that everything is written in C++, so we will not ask you to fill any code. It's more sort of a presentation than a real exercise, and really the focus here is on how to develop this type of application in general. So what is the mindset, what are the steps that you should follow to have a successful development of these things. So let's start by the definition of the problem. So in projective ICP, which is also called projective registration sometimes, we have a set of 3D points in a word frame or in a fixed frame in general, and then we have a set of 2D image projections of those points. So we can see those points through a camera. We will see how the camera model works in a minute. And as usual, in least square problems, we have to minimize some sort of error, some sort of cost function. And in this case, the cost function will be the so-called reprojection error, meaning we will take the 3D points, we will project it into our image, and that will constitute our prediction. And what we are going to minimize is the distance over the image plane. Okay? We will see how that's defined in a bit. By minimizing those errors, so this reprojection error, we can find the relative transformation between the observer and the word frame such that the projections on the image is aligned with the 3D points in the sense of the projection, of course. And for this exercise, we will also assume that the data association is not known, meaning we don't know which 3D point generate which observation. Okay, so that's the setting. Now let's go to the outline of the presentation. While facing this problem, we can basically identify 3 components, roughly. We need for sure the camera model, so that's a sort of a function, we can imagine it, that maps 3D points to 2D image coordinates, and that's the first module. The second module performs the data association, because we don't know that. And the third module is the one that performs the optimization. So in this really simple problem, we can already identify 3 things. And these are the ones that I'm going to present together with the development workflow, more or less, okay? And as I said, everything is in C++. So how will you proceed in a problem like that? Typically what happens is that you're facing a problem and you start to write code and you directly think about the complete system. So you write everything, then you start to use your program or to test your program and something is broken. The problem is that you don't know where to look at. So you have to rehearse basically the whole code, searching for the bug, okay? Then you solve that bug and then another bug came out and you have still to rehearse the whole code because you don't know which module is causing the problem. What we propose here, and that's a general methodology that we try to follow as much as possible, and it's also used in company, is to kind of divide and conquer the problem. So we're facing projective registration. We identify 3 distinct modules. So we are going to test each individual module by its own in a sort of sandbox. So we will test just its functionality without considering everything else. For example, we have to test the least square machinery. So in that context, we will assume that the data association is perfect. So we are not going to test together the data association and the optimization. We will focus just on the least square machinery. At the same time, when we're going to test or to validate the data association module, we will assume that the projective model is perfect, okay? To do so, you have to construct a sort of sandboxing for the module. So that's typically a simulation environment, synthetic data, whatever you want to call it. And this simulation has to be designed in such a way that it's really easy to debug your modules and to visualize the outputs, so that you can really immediately understand what's wrong with your code, okay? So following this strategy, we will basically take these 3 modules, implement them, then perform a validation step after each test, let's say. And once we finish with all the 3 modules, then we integrate all the components and we will perform an extra test, an extra validation step to verify that not only the 3 modules work perfectly by their own, but they also communicate between each other in a consistent manner. So the whole system should be able to work in the real context, okay? So at first, let's design a simulation environment. We are working with the camera, so with image, like we have a visual feedback. So a first idea for the simulation will be just to throw a set of random points in a 3D environment and then test our modules using those points. What's the problem with that? It's not really easy to visualize the output. In which sense? I am testing, for instance, the camera model in this context, right? So I take a picture of my simulated environment, but that's constituted just by 3D points. So I really don't know if what I see is what I should see, right? I don't really have a visual feedback. In this case, we're going to follow this type of reasoning, which is, if I'm working with the camera, what I can recognize really easily is a fixed shape. Like, for instance, if I put a cube in a room and I just take a picture of it and I see the cube through the image, I know that the camera is perfectly working. There is no distortion, for instance. If instead I start to see some really bad shape and the lines start to be curves and strange stuff, I immediately know that something is wrong. While if I have just random points, I cannot observe this type of distortion, for saying. So in this case, we are not going to use the cube, we will use a set of segments. So we just spawn some lines in our synthetic world, and we will draw random points onto these lines. So we will create sort of a segment. Why? Because if we should see a line, and we see a line, everything is fine. If we start to see curves or strange shapes, we immediately know that our implementation of the camera model is broken, okay? Also, this simulation is sort of realistic in the sense that when you're working with vision in general, like visual odometry, position tracking, whatever, so basically you are tracking some salient point in the environment, so something which is really distinguishable over different frames, and those are typically the age of the objects, right? So if I have a comb for saying, most probably I will track the border of the square shape in front. So that's sort of realistic somehow. Now, once we design the simulation, we of course have to implement it. So you should find the code on your repo. It's called pointutils.h and .cpp. For this specific code, I will not go in because that's really simple. You can see it by your own. We will see all the other modules like later in this presentation. And basically those files contain just a function to generate the word, a second function that just spawn a line, and then there is some drawing utils that allow us to visualize everything. So as I said a couple of slides ago, design the simulation, but in general your program to be debuggable, and to be debuggable a program have to be, the output of a program have to be easy to visualize, because the visual feedback is the fastest way to detect a bug, always. Especially in robotics problem when you can actually visualize something. You're not working with the Linux kernel for saying. Now let's start with the first module. So the camera model. I would like to know if there is some of you that never heard about the pinhole camera, because by knowing this information I can go more or less in deep inside this slide. So there is any of you that never heard about the pinhole camera model? I would like to know. Better? Giorgio, is that better? Nice. Okay. I think I'm not live anymore with the chat. So, okay, more or less everyone knows what is a pinhole camera model. Okay. Okay. So I will go through that just really quickly as a small recap, so I will not go in the details. So a camera model is basically, as you know, just a mapping between the 3D points and image coordinates, right? The simplest model possible is the pinhole camera model, which is typically the most used one. And in this model, basically we have a camera frame, which is interior to the camera. And then we have the image plane, which somehow represent the lens of the camera, okay? Just to simplify. This frame and the plane are at a fixed distance, which is f, which is called the focal length. That's actually a vector, so typically you have an x component and a y component, because this vector lies on the plane, zx, okay? So that is, so the parameters are the focal length, the distance between, let's say, the frame of the camera and the lens, just to simplify. Then we have a second parameter, which is the point of intersection between the camera frame and the image plane, okay? This point of intersection is called center of projection or principal point, or in 300s other names. So how the projection is working? As you can see, basically between the 3D point and the camera frame, there is a ray or a line which is connecting the two, so image projection and the 3D point. And that represents a ray of light which is coming from an object and is basically turning on a pixel. Let's imagine it like that for simplicity. So how the projection is working, we know that the point lies on the same line, so the difference between the 3D point and the image coordinates is just a difference in the depth. And we know that the point lies on the image plane, and if it lies on the image plane, it have to be a distance f, so the depth must be f, okay? So the P-norm model basically goes by rescaling the depth of these 3D points so that is equal to f, to the distance between the center and the image plane. And that is what you see here. You take the original coordinates divided by z and then multiply it by f. That's basically the trick. This 3D point is then referred to this center because it has basically the same reference frame as this guy. So we have to shift it so that is expressed in the reference frame of the image, which is this corner over here, so top left. And that's why we add the coordinate of the center of projection. So just a really quick recap. So that's the complete projection, okay? How we can model it in a more, let's say, systematic way? Really easily, we put all the intrinsic parameter, so given the 3D points and the intrinsics, I can determine the image coordinates. You can put all the intrinsics in this camera, which is called the camera matrix. So the 2F, in this case, they are the same, but in general, they can be different, even by a lot, and the principal point. Then you take the point in the word and multiply it by this guy. So you retain f times x, f times y, and blah, blah, blah. You have to rescale by the z, so you divide these two coordinates by z. Wait a sec. I have some problem with the connection. Okay. Sorry. So you will rescale this point by the z, and this operation is called homogeneous division. So the complete projection, you can figure it out by, I take a 3D point, multiply it by the camera matrix, and then perform the homogeneous division. And that's the pinhole camera model, okay? Now, in general, the 3D, in this case, we assume that the 3D points are expressed in the camera frame, while typically, what happens is that we have a camera placed in a certain location in space, and the points are expressed in the frame of the word. So typically what we have to do is we have to take the points in the word, multiplied by the transformation between the word and the camera frame, and then we can perform the projection. So multiply by k, perform the homogeneous division, okay? And that is for our sensor model. I would like just to point out that while from a 3D points we can exactly map to a precise image pixel, let's say, the opposite of course is not true, because at maximum what I can determine is this ray by inverting this relation, but I cannot recover for the z, right, because I fixed the z to be equal to f. So given a 2D image of projection, I cannot get the 3D point. What I can get is a ray, so a direction from the center that pass through the image point, which is in the direction of the 3D point, but I don't know exactly at which depth, at which distance onto this line, okay? And that operation is called unprojection. We will not see it in this presentation, but you will see some variant of it in the next lecture with Giorgio, okay? So that is our sensor model. So we need the camera matrix, the transformation between the observer and the word, and we have to know how to perform a division, basically. Now let's go to implement it. That's a typical flow when you're developing a module. So you first define the mathematics, and then what I suggest personally is always to write the implementation, at least the abstract details, on a piece of paper, because that is really helping you to focus on the details and to understand what you really need to implement that specific functionality. And also it avoids that then later on in your development you see your modules and you realize that this attribute should not stay really there, this functionality is not really consistent, etc, 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 etc. So that is what I do in this slide. I just like write what is really required to implement this really simple sensor model. So as we said, we need the pose of the word with respect to the camera, the intrinsics parameter on the camera, of course, and then the only functionality that we really need is a mapping from 3D coordinates to 2D image points, okay? So that is what we are going to see in camera.h and camera.cpp. Until now, there is something which is not clear, like about for saying the pinhole model. Giorgio writes something. There is something that is not really clear in the presentation until now, while I'm opening the CPP code. Okay. So source. Okay. Nice. Now, the class is of course really simple. That's the constructor. So you are passing a bunch of parameters to initialize the object, and you can construct it just if you pass those parameters, right? And as we said in the presentation, we have a camera matrix and a word to camera pose, right? Now, I didn't get what is the X in slide 11. Is the pose of the word with respect to the camera, okay? So is a transformation matrix, in fact. So should be this guy over here. That is the X. Now, other than what we see in the mathematical definition of the problem, we have other parameters involved, or better, some other consideration that we have to make. Now, in the mathematical definition of the pinhole model, we assume that we can project any 3D point, and in whatever position they are, we will see them through the image, because our image plane is infinite, right? From the mathematical standpoint, okay? But in fact, in real cameras, you know that you have a limited field of view, which is reflected in the fact that actually your image have a fixed size, right? So that's the dimension of your image plane. So while you are projecting a point, you have to check inside your program that the projections fall inside the borders of your image, inside your field of view, basically. So in fact, we have a couple of extra parameters, which are rows and columns. So you can imagine the image like a matrix. And those also corresponds to coordinates. I guess that in the OpenCV world, you have the rows are the y's and the columns are the x, okay? Okay, that is. Also, another consideration that have to be made is that we cannot project points that are behind us, right? Like if I'm looking forward and I have something in my back, I cannot see it through the camera for sure. While in the mathematical model, that's not specifically written, okay? So to model a real camera object, we have also to take into consideration that once we transform the 3D point from the word frame to the observer frame, we have to check that the point is in front of us. Because as Giorgio just pointed out, because the image is a little bit confusing, the Z is typically in front of you. So if the Z coordinate of the transformed point is behind the observer, we cannot project that point, okay? So that's what we are going to check here. So we will check for the depth once we transform the point, and then once we project it, we check that the X and the Y coordinates are inside the borders, basically, okay? So inside our image. That's a function that just projects a 3D point. So given a word point, which is a const, of course, because we don't have to modify it, returns me an image point. And we will follow just the step that you see on the slide. So multiply it by the word to camera pose, apply the camera matrix, perform the homogeneous division. Those are operations that are carried on by, we use the eigen library here, but I will not go to details in that, okay? So that how is implemented the projection of a single point. To project multiple points, we just will pass a vector, and then we call this function for each individual 3D point. Really, really, really easy. those are some setter and getter that we implement. Okay, so we have basically a couple of extra parameters, which are the rows and the columns that represent the image size. Okay, so let's come back to the presentation. So once we have implemented this fantastic function, by taking into consideration both the mathematical definition and some concrete details, some real world details, we are ready for the testing part. And the testing will be like really easy. We will just construct a simulated environment made by our fantastic lines. We will place the camera in a certain location, and then we will just move the camera around. And what we want to check is that lines remain lines. We don't implement some strange stuff for which lines start to become a curve, and we don't introduce any weird distortion. Okay? So let's go into see it. I will also show you how to compile this program. You are in this folder, so 24 Projective ICP. You need to construct a build directory. Okay. Then you go inside the build directory and you call cmake.dot. It's out of the scope of this course to explain you what is a cmake. I will not go into that, but it's basically, we can just say that it's a layer of abstraction above the make file. So it's not actually building your program, but it's generating the files that are used then to build your program, just to put it really simple. So call the cmail, it generates the build file, so now I can compile in the usual way, so I can do make, and it will compile everything in my project. Okay? So that's typically what you have to do in a cmake C++ project. Construct a build directory, go in the build directory, cmake.dot, and then you have to call the make or the make install or whatever to actually compile the files. Now, of course, it will take like ages because I'm stupid. Make -J4. Let's go to see that. Let's see. You can try to compile it also on your own, so that eventually when I'm running the test, you are running them also, and you can better see what's going on. Okay? If you want, of course. So now I am in build. I will go to executable and I will call my test. So ./camera test. Okay, so that's the simulation. Now with the WASD combination, like in games, I can move around. So with W I can go forward. I can turn left and right, whatever I want. Now we also report here the time of the projection because we want to make sure that everything is also efficient. We are doing the test, so we take the occasion also to check efficiency. And everything is fine, as you can see. Okay, that's really easy to visualize. Nice, so the camera models seem pretty fine. Now let's go to the next step. The next step is data association, right? Now we have 3D points and 2D observations. We will make a couple of assumptions. The first one is that we have available a decent initial guess about the camera location, and that the points are sparse enough, which means that the image will be, I don't know, size 300 by 400, but the actual points that I'm observing is just a subset of all these possible pixels. So the observation is pretty sparse. By performing this assumption, we can approach the data association problem using a nearest neighbor strategy. So the dummy version of it will be just to take all the 3D points projected into the image, the ones that can be projected into the image, and then take the closest point in the sense of the distance in the image plane. Okay, so I have to check for each 3D point which is projected times the number of measurements that I have. Okay, So that is a solution. Of course, it's really dummy because an implementation like that would take ages to give us the proper correspondences. Like if I have n 3D points projected and n measurements, this will be my cost, O of n square. Okay. So to speed up things, we can approach the problem by using a distance map, because in fact we have 2D observation, so our problem is a low dimensional problem first. Then we know that the measurement is not changing during the least square iterations. So what I can do is that I can construct a distance map at one time, like when I receive a measurement I will construct a distance map, and then I can just querying it after each iteration of least square, because querying a distance map is really fast, is actually O of 1, so it's a constant cost. So that for me is fine. Why I have to consider the fact that the measurements is not changing? Because if instead I construct the distance map on the projected points, those points are changing over the iteration, right? Because I have to take the 3D points, transform it, project it, then I will perform the iteration of least square, but at this step, the transformation will be different, right? Because I update my estimate. So then I will have again to transform the points, project them, compute the distance map, and repeat over and over and over again, okay? So it's smarter to construct it into the measurements because that will not change, so I will amortize the cost of the construction of the distance map. So that's the mathematical background, let's call it, not so mathematical, but more or less. Let's go to the implementation design. So I'm constructing the distance map over the image by using my observations. And at each iteration, I have just to basically query the distance map. So those are the things that I really need. So the attributes will be the image size, because of course if I'm constructing the distance map over the image, I need to know the size of the image so that I can construct the distance map with the proper size. I need the image points. Those are not really an attribute, I will call them more an input to the module, but let's say it's an attribute. And then I have to define a threshold, which is max distance, because of course I don't want to associate points which are really far from each other. So in this sense, I'm performing gating while I'm using the distance map. I will not use best friend and lowly best friend because it's not required for this example, but by just thresholding, we will see that everything is fine in our case. Then what are the functionalities? Given the 3D points, compute the distance map, that's for sure. And then we have to define a function which is which give us the possibility to query the distance map. Okay, query for correspondences. Okay, I will show you the implementation, then we will go directly to the test. I will just do a short presentation of how the test is made. You're basically placing the camera in a certain location, taking a picture of the lines that you have in front, and using this picture you construct the distance map. Then you basically constantly reprojecting the point in the world, and you have always the capability to move. So while you are moving, the reprojected points can fall or not inside the distance threshold of your distance map, and you can visualize the correspondences and see that everything is consistent, right? So let's go really quickly to code, just to the header file to make things easier. Distance map.h, I guess. Yeah. Everything is here, right? Yes. Okay. So a distance map, as you know, you can see it as a metric structure. So at each coordinate rows column, you have a certain cell. And what we need in a distance map cell is the identity of the parent. So the identity of the cell that generate the distance map cell. Okay. So the points in the image, in this case, the measurements. Then the distance from the parent, because we have to check that that not exceed the max distance. And then we need the corresponding row and column index, because those can be always useful. Okay. So in a distance map cell, we will have a map cell to the parent. the distance, and the indices. Okay. Here is also added the weight, which is used basically to weight differently depending on the distance, but we will skip that for now. Okay. Then that is the distance map. Okay, and it's constructed using an eigen matrix object, which is just a matrix. Okay, using the cell as an element of the matrix. Right. Now, given a cell, this guy returns me basically an array of distance map cells, so the neighbors basically. Okay, and here is how to perform the compute. I need my input image, which will have a 1 in the point in the coordinate that correspond to a measurement. I need to pass through it the max distance, and then as an output I want the index map, which means if I query a cell, I want to know what's the closest parent, what's the closest cell. And also I would like to have a float image which represents instead the distance. So if I query the distance image, I will basically get the distance between this cell and the closest parent, so the closest point from which the expansion started. Okay. And here I can just store it. Okay. So you see here int images and float images. Those are just really matrices where we have a type in the cell. Okay. So the cell in IMAP is just an integer. Now let's go to see the test. Build executable. Correspondence finder test. Okay, so that is the guy. In this test we'll have the capability also to expand or diminish the distance map expansion. If you press plus or minus, you will see how the max distance is reduced in this case, and like here I should be able to increase it again. And by using the SWAD combination, I can basically move it. I can move around and see which point will be associated. As you see, that is like effective, and it works just if I'm really close in this case. I will try to start again the program. Okay. I can move around and see that the associations are consistent. As you can see here, everything seems pretty fine. Of course, if I'm going too far, then everything starts to break up, because that's just a nearest neighbor strategy. Okay, but for the cases where I'm pretty close, which are the ones that I'm interested in, because I assume to have a good initial guess about my relative pose, everything seems to work quite fine. Okay, so also the correspondence finder, it's pretty good. So we verify the camera model, and we visually verify the data association. So we just need the third module, which is the least square optimizer, basically. Okay. So in the least square optimizer, we have to define the state and the measurements as usual. I will not go through the state because that's exactly the same as in standard ICP that you just saw with Barbara a lecture ago. The main difference is that we have 2D measurements, right? Because we have just the projections of the point in the image. So actually the measurements are in R2. Everything else is the same. So that's a SE3 object. I parameterize the perturbation as a 6D vector, and I apply the perturbation by taking the V2T and multiply it by the left of our state. Now let's go to the prediction. Of course, the prediction is just our sensor model. Okay, so we will take just a point, multiply it by our transformation matrix, and then we will perform the projection. So camera matrix and homogeneous division. Of course, we can recognize that if we also isolate this piece, that's exactly the prediction of the ICP problem, right? So, and we call that P hat. Okay, so P hat is actually the prediction of ICP, just a multiplication by a transformation matrix. We will define another intermediate quantity because it's useful, and we will see why in a minute. P hat cam, which is just the transformed point multiplied by the camera matrix, but without performing the homogeneous division. Okay? So that's our prediction. So we define it through the model. And that's our error. The measurements, as we saw, are real, so they belong to a Euclidean space, so a straight minus, it's more than fine. And there it is. Prediction minus measurements, okay? Assuming to have the correspondences between n and m, which are the indices between the 3D points and the measurements, okay? And that's our error while we are box plusing it for the derivation. Now, to compute the Jacobian, which is really straightforward in this case, we will exploit the chain rule, right? So let's start by dividing the prediction in pieces so that we see how many derivatives we have to do. We can immediately identify that there is the homogeneous division, the projection, let's call it the proj function. Then we have a linear transformation, basically, because K is just a straight matrix. It doesn't belong to any particular space. So that's just a linear transformation. And then we have a rigid transformation by the transformation X. So we have actually three pieces, and this, of course, will reflect inside our Jacobian computation. So we will have the derivative of proj with respect to its argument, which is p hat cam, as you can see here. Then the derivative of a linear transformation is just the coefficient matrix, as we know. So the second piece will be just K, we don't have to do anything. And then the third component will be the derivative of a rigid transformation, let's call it for simplicity, which is exactly the Jacobian that we have in the ICP problem, right? So what we actually have to compute in projective ICP is just the derivative of the projection with respect to its argument evaluated in p hat cam. Okay, I hope that's obvious for you. Okay, so those are the pieces. So that is the Jacobian of proj, then I have the linear transformation through K, and then I have the Jacobian in ICP. This one you already see it with Barbara, and is this guy over here, where p hat is always the transformed point, okay? K is a constant, so we don't worry about it, and then we have just to evaluate jproj. Now jproj is just x over z and y over z. So intuitively, if I take x over z and I derive it over x, I will just obtain 1 over z, the same for the y over here in the second coordinate. Then I have x over z derived with respect to z, so by doing just some power derivation, is minus x over z square, and the same, of course, apply for the y. So that is the block that I was missing. So by multiplying the three, I will obtain the Jacobian for my error function, okay, in this case. Everything is clear here? I think I am in a huge delay. Okay. Nice guys, thank you for the feedback. Then, let's go to implemented, or better, to design the implementation that we are going to implement it. So that's a least square solver, so let's figure out what we need. For sure we need the input data, that's pretty obvious. So we have the word points and the image points. As usual, those are not really attributes, those are more inputs, to be honest with you. Then we need the current estimate about the camera pose, right? So the current estimate about the transformation between the word and the observer. And we will also implement some form of robust kernel, because that is always useful to have in a least square solver, right? So those are the attributes. Then we have the functionalities. We have an initialization functionality that basically clear the solver, let's say. So it cleared the H matrix, the B vector, and blah, 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 blah. So it's just a sort of a reset, we can call it, because that's useful. And then we implement just a function that performs a single iteration. So given a set of correspondences between the 3D points and the image points, it solve the linear system basically and apply the perturbation for a single iteration, right? So we will check that in PICP solver, Projective ICP solver, in a minute, but I will introduce also the test. So in this case, we have to test our least square solver, and as I tell you at the beginning of the presentation, we want to sandbox the functionalities. So everything is in simulation, so we can provide to the solver perfect correspondences, right? Because we know which point generate which projection all the time, okay? So we will just place the camera, take a first picture, then constantly reprojecting the point, we can move the camera around. Once we find the location that we like, with the space bar, we will perform a single iteration of least square and see how the system reacts, okay? So let's go by step. So at first I will show you the header of the PICP solver itself. Where it is? Oh, Jesus, no. Yep. PICP solver. So we have our init method that basically we pass the camera, the word points, and the image points. Those are sort of the data that we use. Okay, really simple. And also it resets the H matrix and the B vector. We implement a setter and a getter for the kernel threshold, like really straightforward, and some other things that might be useful, like I want to access the camera to see that the camera is actually there. I want to know the key of the inliers, the key of the outliers, so all the points that are, let's say, outside the kernel width, number of inliers, and that's how we perform a one round, okay? So we will pass a set of correspondences. In pair is just a pair of integer, which you can implement in C++ using the std pair struct. And we have a vector of those. So the first index will be the word points and the second index will be the image point, I guess, or the other way around, but it's the same. And then here there is a function that says, okay, keep the outliers or not, meaning if a point is outside the kernel threshold, let's say, just discard it, like throw it away. If that is false, if it's true, we will just rescaling using the value of the kernel and we will include it inside the optimization. So with this parameter, you can basically put the kernel threshold at its extrema, the robust kernel at its extrema, and say, okay, if you are outside, cancel it, basically, okay? Then, of course, we have the error and Jacobian function that, given the word point and the reference image point, will compute the error and the Jacobian. So that's 2D vector. This is a 2 times 6 because the error is 2 and the state is 6. And here is a linearized function, which is the one that accumulates the contribution to the H matrix and to the B vector. So it's basically constructing the linear system, okay? While in one round, we will solve it. And those are the parameters that we just talk about. I will not go in the implementation for all the modules. If you know a bit of C++, it should be easy for you to read. If you don't know it, we really put a lot of comments in it, so it can be a good occasion to have a first touch with C++, with something that you already know and you have just to focus on the syntactic and on the semantic of the code, okay? So that was the PICP solver at the abstract level. Now let's go to the test. Next, okay. So if I move around over here, you see that I get perfect correspondences, right? Over there. Then if I press the space bar, I will just perform a single iteration and I should be able to estimate my transformation, as you see. Now, for the fact that our observations do not fully define a 3D point, right? Because we know the point. Yeah. Yeah, I will show the solver. Let me finish to say what I was saying. For the fact that you have a 2D observation over here, there are conditions when even if you have a perfect, how to say it, perfect association, the convergence might be slower, okay? Because the 2D projections are not enough to determine a 3D point, right? Because you know them at up to a scalar factor, which is the depth. So that's a pretty tough problem to solve, actually. And we will see that without perfect correspondences, it's even more hard, okay? So let's come back to the CPP solver. Over here, so that's how you compute the error and the Jacobian. I hope the code is, I think the code might be Cyrillic for you, but I will try to go to it to make it a little bit clearer. So we already see the camera project point function. So what we say, okay, I want the predicted image point. I will pass it through my camera together with the word point. So this functionality takes a 3D points and give us as an output the predicted image points. It is also telling us if the point is good or not. So if the 3D projection falls inside the image plane or outside, or if the point is behind us or in front of us. Very easy. If the point is not good, just return false because we cannot compute the error and the Jacobian for such a point. The error is pretty straightforward, and then here we have to compute our fantastic Jacobians. We take our word to camera pose, which is contained in the camera itself, multiply it by the word points, and this will give us p hat, okay, actually, p hat, which here is called camera point, to increase the confusion, of course. And that's the first component. So while having the camera points, so the p hat, we can already compute the Jacobian for the ICP, right? Because that's everything that we need, so we are going to do that. That's an eigen matrix, okay? So the type is a float, and you have 3 rows and 6 columns, and that's just the eigen way to initialize a matrix with all zeros, right? Then we will extract the corresponding blocks and fill it with what we need. As you see with Barbara, the first 3 columns and all the rows are the identity. The second one is the skew of the transformed point that here we implement with the function skew, okay? And that's how you place a block using the eigen library. Then we have to compute the JProj. To do so, we have first to compute the p hat cam, so taking the transformed point and multiply it by the camera matrix to obtain a FOM. Inverse of the depth, because that's what we need for the computation, and it's square, okay? And then we just fill the JP, which is a 2 times 3 matrix, which is just the block that represents the derivative of the proj function. Fill the terms and then multiply everything to get the Jacobian. So JProj, camera matrix, JICP, okay? And that's the linearized function, which is written in a really octave way. So there is nothing new here, I guess, for you. This is how you reset the matrices in C++, so just set it to 0. Then for each correspondences, we will take the error vector and the Jacobian matrix, take the correspondences, like for the word point and to the image point, call the error and Jacobian, which will fill for us the E and the J matrices, check that everything is inside, so the projection goes well, we don't have points behind, and everything is inside the field of view of the camera. Once we check that, we can compute the chi-square, so E.E, basically. Define the lambda, and here is how we apply basically the robust kernel, which is the usual one that we see also in Octave, where we are basically rescaling all the points that are above a certain threshold to have an error which is exactly at the threshold as null. Okay, and there it is. Then here is how we compute the linear system. So we add the contribution j dot transpose times j times the lambda, which is the weight factor for the robust kernel. So here we don't consider any information matrix. We can assume that that's just the identity. So, and this is how you fill it. One round, what it's doing is basically constructing the linear system, adding a damping, which is prefixed here, and that is required because, as I tell you, your observations are just 2D. So the problem is not always really well conditioned. So we will add the damping to make sure that the H matrix is positive definite and even more non-singular. Okay. So that's plus equal. And then here is how you solve a linear system using eigen. So you take the H matrix LD-LT, means the Cholesky decomposition with diagonal. So you have LD-L transpose. Go to check it out if you don't know it, but it's just a variant of the Cholesky decomposition, nothing spectacular. And then you do dot solve with your coefficient vector, so minus b. Once you get your perturbation, you just apply it and assign it again to the camera. So you do set word to camera pose, take the v2t of the dx and apply it to the previous value of the work camera. This is written in a horrible way, but I think you understand the sense of what is written. Okay, so that is the implementation. But of course, like if you are writing like proper C++ code, that's really a lot octave-like, just to make everything clearer for you. Okay, but of course you can do different stuff in C++. So that is the code, and we already see the test really quickly. So we are basically close to the end. I just want to give you some extra hint on the implementation of the least square part. The easiest thing to do is always to verify the error function and the Jacobian. The easiest way to do it, sorry, is to place your system at the optimum using some syntactic data and verify that the error at the optimum is 0. So the error at 0 should be 0. That's the dogma. Meaning if the error function is properly written and the system is in an equilibrium configuration, the error should be 0 if it is at the optimum. Furthermore, if you perform a least square iteration while you are at the optimum, the system must be fixed at the optimum. It should not oscillate or go away from the minimum and diverging. So that's a really easy test that you can always do. Like write your error function and your Jacobian, place the system at the optimum and perform some iteration of least square. If everything stays fixed, most probably, or there is a high chance that your error function and your Jacobian are well written. That's not always the case, but it's a really easy test to do and it's really informative for your development. The other suggestion is to use numeric Jacobians at first. This we already say it, but if really speed is required, so if you have performance issues, then you have to use analytic Jacobians. What I typically suggest to you is that if the problem is really easy, so deriving the cost function is not really a pain, and that typically happens for registration problems like whatever variants of ICP you see, then compute it directly in an analytic form and use the numeric Jacobians to verify your computation. Because maybe you're spending a little bit more effort in the derivation, but the problem is simple, so also the errors that you can make are really simple to debug, as a general rule of thumb. Okay. Let's put everything together. So basically we will have the camera model, the data association will be on, and with the spacebar we can perform a single round of least square, so updating our estimate. Okay, so let's go to see it. Okay, so we have our usual setting. So the first picture is just the observation, and then we constantly reprojecting the point, and we can move the camera around to see what happened. So for instance, if I go that way and then I press spacebar, look how slow the convergence is, but then I'm able to reach it. Okay, that's the exact convergence. I want to show you that, of course, if I'm too far and the problem is not so well conditioned, sometimes I can be fixing some local minima even. I think even in this case it should be able, but look how slow is the convergence. That's the local minima. I cannot move anymore from here. Why is that? As I told you, because your observation are underdetermined, and also you're using a nearest neighbor strategy, which works really when you have a proper initial guess about your problem. So in every least square problem is like that, but specifically when you are working with cameras, that it's even more important, because the problem here is even more non-linear than in classical ICP problems. Okay, so maybe let's try to fix it, just because I hate to see it like that. Not even. Whatever. I find the configuration that broke it. Whatever it is. So you can play around with it to have some feedback to see how these things are actually working. Okay. So conclusions. The message here is, when you have a really difficult problem to face, and in robotics basically all the problems are difficult, apply always a divide and conquer strategy. So divide your problem or your system in small parts that are easy to solve and to debug also as a consequence, right? Then sandbox the individual components, so test them individually and make sure that everything is working as you design it. Once all of that is completed, then you can integrate the different pieces and you can understand if the system would work in the real context, and that all the modules communicate between each other in a consistent manner, let's say. So that was all for the presentation. I don't know if there are any questions. There are any question other than the one that I just saw from Akash? The main? What do you mean, Giorgio? No, the test should be in the executable thing. So here is the main. Those are basically the limits of our synthetic world. That is the function that just construct our simulators, and we print on the screen how many points did we have. We define our camera matrix with whatever value is it, and the sizes of our image over here. Initialize the camera, take the reference image points, and just project the points using the camera. Okay, as I told you in the presentation. So the first pick is generated like that. Then we have our correspondence finder. We initialize it using the reference points, because we say that the distance map is constructed using the measurements, and we will measure the time. Then we take the pick solver, and every time we press a key, there is an action, of course, depending on the specific key, but we can draw the distance map, draw the points, check for the correspondences. So every time we will reproject the points over here, draw them, and draw the correspondences that we get from the distance map. We will show the image, and here is how we control the motion depending on the key that we press, right? We can increase or decrease the expansion of the distance map. And here is how we perform when we press the spacebar, the least square iteration. So we will initialize the solver and perform one round. So it's just one module, one after the other called. That is not really integrated in a system, in the sense that as you see, the modules are like still divided. We are just testing the functionality altogether. Most probably then this module have to be integrated in some sort of box that is performing this projective registration problem. So these are still pieces that we just put one after the other, okay? But that's more or less how it goes. It's straightforward with the presentation of the slides. Here inside the draw functions, you can find some reference to OpenCV, which is the computer vision library. In this case, we use it just to visualize images, but it's much more powerful. So if you are interested in these topics, it might be useful to have to go to look at it. And that is, I guess, that is. No other questions, guys? Okay, Giorgio, I will switch to you. Are you ready? The ICP scala. What do you mean by ICP scala, Giorgio? ICP schema. Yeah, sure. Let's go over where it can be well explained. I can rerun the test so you can watch it directly from there. Like I will use the test to explain it. Okay, so while we are performing the least square iteration, you will notice it like that. If I press the spacebar, I will perform a single iteration, and I will move basically the projection of my 3D points, right? So it means that all my query points will be modified because I will have different coordinates for them, right? Because I'm transforming using a different transformation. So I have basically to requery my data structure. I have to requery my distance map to get new correspondences. And this will become evident the more I press the spacebar, right? Because those projections will change and change and change and change and change. So this allows also to boost convergence, right? Because the more I get close to the real minimum, the more correspondences I should have, so the more I enforce convergence for my problem. Is there any critical missing? Performances. Francesco, performances. Like if you implement in Octave a real system like that, it will never run in real time. There is no possibility. Other than all the other things that you can do in C++ that you cannot do in Octave, like templates, moving semantics, and so on and so forth. There are hundreds of things. But the main reason is performances. And the same applies also to Python, guys. Like when you have to do time critical application, Python just cannot be used. Yeah, like if you have to implement this sort of projective registration on a real system like the Oculus Rift, for saying, you cannot do it in Python because you will basically exceed sensor rate constraints, so that will just not work. So that is the schema, and that applies to all registration problems. So after each iteration of least square, while you are performing ICP or whatever, you have to recompute the correspondences, because one of the two clouds will change its coordinate in the corresponding reference frame. So the query that you performed at the step before is not valid anymore. Maybe that correspondence changed because its distance with the measurement will change, okay, after an update. Giorgio, I will switch to you. Maybe even, I don't know. Yeah, as the professor says, the efficient things in Python are calling in C++, but even the things there are C precompiled, but then there is a lot of wrapping in Python that still make you lose some performances, even a lot of performances sometimes. So anyway, I will switch to Giorgio so that he can introduce you to computer vision, if there are no other questions. Sorry, I'm not sure I understood how the distance map works. Yep, that's exactly what we do. So you understand it? Or there is another point that is not clear. We constructed on the observed point, project the word points, and use them out to assign. Yeah, that's correct. While the observation are never changed, right? Not because the camera is fixed or not, because what you are observing will not change over time. Like the word is like, we fixed the time, basically, right? So we have this observation and we have to solve this problem. So we will fix the time step and we will solve the projective registration problem. That's why the observation is not changing. Okay. Giorgio is starting his explanation. Giorgio, I will stop the streaming if I don't see any other guy question. And so you can switch on and start with the epipolar geometry. Joe, switch the streaming.